Okay, so I have two goals for this video. One is to continue with increasing our complexity of our analyses. And the reason that we're going to do that is because the complexity of the research designs changes. And so we need to respond to that. And I'll explain that in a minute. But I also am hoping that by discussing the complexity of this next example, of this next analysis, it's actually going to reinforce what we learned about t-tests. Okay, and so let's go. Let's get into it. All right. So let's suppose that I'm interested in whether or not listening to music disrupts cognitive performance. And in this case, I'm thinking of people who listen to music while they study or read a textbook or whatever. And, people could get into a discussion about whether or not that's disruptive to your learning. And so I might bring that into the lab and talk about, and try to collect some data that would speak to that issue. Okay, so the basic experiment, I think, is easy to think about. We could have two groups, right? Some of the people are put into a group where it's quiet, where they can read their textbook or do whatever, and in another group where there's music playing. Okay, and in order to make this a simple experiment, let's have people, we'll present them with a list of words via a PowerPoint presentation, for example. So maybe a list of 30 words that are presented one every second. And then we're going to ask people to recall those words after they've gone through, 3 or 4 or 5 presentations. And I'm going to have some of the people in a quiet room and some, or maybe have noise canceling headphones, and another group listening to music. And then basically what you would do then, I think we can anticipate what the data would look like, right? So we're going to have people in the quiet group and people in the music group, and we'll maybe keep track of how many words they remember from the word list. Okay, so maybe people are. I'm going to keep it simple here, folks. Okay, I'm going to keep it fairly simple, just so we can talk about the conceptual bases of our analysis here, but it won't be sort of mathematically that challenging, I hope. Okay, so 5 people in this group, and then the people in the music group, let's say that we see people remember this for the number of words in that group. Okay, now we can think about we can look at this and maybe make a guess about whether there's a decrease or not. We probably want to do a t-test here, right, for our statistical analysis. The problem is the design is a little bit flawed. And by that I mean it's not complete, okay? Lots of people are interested in the influence of music on a lot of things, on mood, on studying. I tend to, when I teach research methods, a lot of students want to do this as their project. But here's the deal. Even if we found a decrease here, and of course we're going to look at the means, right? The mean for the quiet group and the mean for the music group. And let's pick some music, okay? It could be anything. Let's say this is Taylor Swift music, okay? You may be a Taylor Swift fan or not. It just doesn't really matter. So let's do this. Taylor Swift, just because I don't want to have an M there. It's a little bit confusing. And we're going to compare those means, right? And of course, we would expect that we're going to need to get the sum of squares for these two groups. And I'm hoping that this is review in a way, right? But here's the problem. When we talk about Taylor Swift music or whatever music you want to listen to, whether it's Grateful Dead or Taylor Swift or Peter Gabriel, that's one of my favorites. The problem is when you have lyrical music like this, it's a conglomerate variable. Because if we see a decrease from the quiet to the music, then I don't know how to interpret that, because I don't know if it's the music itself or whether or not this group is just in a non-quiet condition, right? Even if we see a decrease here, I don't know if it's because of the music or the fact that these people are in the quiet, these people are not in the quiet condition. So as a researcher, I need to add another group to this experiment, okay? It's not because I want to make things more complex, it's because things are complex, okay? And that's how it works. The complexity that we keep adding on in this class is because research is a complex enterprise. It's not just simply two groups. We couldn't interpret our data. Even if we saw a statistically significant decrease, we couldn't really interpret that as being attributable to the music. It could be just the noise. So we're going to add another group here, and it's going to be a white noise group. And white noise is something like staticky, like a fan, like a television without being on a channel or a radio. Okay, it's kind of this like... And little piece of trivia for you, it's called white noise because it contains a lot of different frequencies of sound all put together. Just like white light is composed of lots of frequency of light. And how do I know that? Well, we can just get a prism and make a rainbow. All of those frequencies go into making white light. So people have referred to this combination of lots of frequencies of sound as white noise. Okay, so that's the little piece of trivia. Now, I want to talk about, again, this is a research methods issue. We will get to the statistical analysis, but the research method issue here is that, well, I'm going to be able to interpret this group much better if I have the white noise group, because if we see a decrease that was caused just by the noise, then we should see that in this group here too. If this decrease is because of the music, then we won't see it here because this is not music, it's just white noise. Everybody with me? There's a logic here to the research. There's a logic here to the research. I need to be able to tease out the different variables here. There's the music variable and there's the noise variable. So this will tease out the noise variable, okay? But I'm also going to add a fourth group, and that is when I'm listening to Taylor Swift music, not only is there a melodic component, right? That's what music is, the melodic change of notes. But Taylor Swift is also singing lyrics. And so it's music plus lyrics, and of course there's noise. So I'm going to also add, this is going to be Taylor Swift music, but we're going to do music without lyrics. So if the decrement here was because of the music, we should see the decrement here, but not here. If it was because of the noise, we should see a decrement all the way across. Okay, so this is how research designs are formulated, because we're trying to figure out exactly the variable that might cause this disruption, if there is a disruption. So let's look at the white noise group, and of course I'm just making up these data, but the groups will create the data from our subjects, and the data then will inform us about, what part of this constellation of variables is affecting people's memories. Okay, so let's do this. Let's do this. Okay, and so we'll be able to get the mean for the white noise group. We're going to need the sum of squares for the white noise group. And then we'll look at the Taylor Swift music without lyrics. And so we just have the melodic component. And so maybe we have something like this. Okay. And then we would be able to get the mean for without lyrics. These are just subscripts here. Okay, these are just subscripts. And so what I'm going to ask you to do before we get to the next video is to do these computations. That is, let's get the means for each of these groups. Let's get the sum of squares for each of these groups. Okay? But before we do that, and please don't start that now. That's going to be your homework to fill in these numbers, okay? Because I want to talk a little bit about the statistical analyses before we do that. So don't be working on that right now. That's for after the video is done. You can work on these numbers. But I want to talk about what kind of analyses we're going to do here, okay? And one of the questions is, well, do we really need to do a new statistic here? Or can't we do multiple t-tests, right? Because right now, I'm assuming that you folks know how to do a t-test. And by the way, let's talk about this as an independent measures or a between groups experiment. So there's 5 people here, there's a different 5 people here, there's a different set of 5 people, there's a different set of 5 people, okay? So why not just do multiple t-tests, right? I could do a t-test here to compare those two groups, right? I could do a t-test here to compare these two groups. I could do a t-test here to compare these two groups. Are there other comparisons that we can make? Well, I might want to compare quiet to white noise, that is this comparison, right? We could do a t-test there. I might compare Taylor Swift to Taylor Swift without lyrics, so there will be another t-test here. Okay. Any more? Well, yeah, there's yet another t-test that I could do, and that's this t-test here. Okay. And in fact, when we have all the possible pairwise, right? That is, by the pair, when we have all the possible pairwise comparisons that we can make, you'll actually see a symmetrical pattern like this, okay? And this is where art and science and math sort of come together. We get this nice little pattern. How many t-tests, how many pairwise t-tests would we have to do all of the possible pairwise tests? 1, 2, 3, 4, 5, 6 t-tests. Okay? So Could you do that? The answer is yes. Well, you better be able to do it, right? Because that's similar to what might come on an exam. I can do a t-test between these two. I could do a t-test between these two. I could do a t-test between these two. Okay? So I could do the analysis by doing, in this case, 6 pairwise comparisons by the pair. Okay? There is a problem with that, however, and that is, remember when we do our t-test, we set up an alpha level of 0.05, and remember we talked about this, that is the probability that we're going to make a type 1 error, okay? The probability that we're going to make a type 1 error is given by our alpha level. So if I do this test, I have a 5% chance of making a type 1 error. Problem is, I mean, that's okay for a single test. The problem is, if I do a t-test here at alpha level of 0.05, and I do a t-test here at alpha level of 0.05, and a t-test here at alpha level, t-test, t-test, t-test. When I think about this from an experiment-wise perspective, that is, when I do all of my analyses, let me ask you this question. Do you think the probability that we're going to make a type 1 error will increase once I do 6 of these, will decrease, or will remain the same as 5%? Well, it's going to end up increasing my chance of making a type 1 error, even though each of these tests I only have a 5% chance. When I do 1, 2, 3, 4, 5, 6, I'm going to basically increase the chances that I'm going to make a type 1 error. If each of the tests is done at 5%, when I do 6, then I'm going to increase those chances. I mean, you know, let's think about a Russian roulette game, right? Everybody familiar with that? You take a gun with 6 chambers in it, and you put 1 bullet in there and spin it, and then, you know, never, ever, ever play Russian roulette, okay? But the chance that you're going to shoot yourself with that bullet, what's the probability? 1 out of 6, right? There's 1 bullet and 6 chambers, you spin it, 1 out of 6. If you played the game once, you have a 1 out of 6 chance of killing yourself. That's 16%. But here's the question. Suppose you play that game 10 times. Do you think you're going to have a higher than 1 in 6 chance, lower than 1 in 6 chance, or same 1 in 6 chance? And I hope that you're able to intuit that the more I play that game, the higher the probability that I'm going to get the bullet. Even though each time I play it, it's 1 out of 6, when I keep playing it, what's going to happen is I'm going to increase the chances of killing myself. Now, making a type 1 error is not nearly as serious as killing yourself, but it's not good to make a type 1 error. It's not good to make a type 1 error. Remember, we talked about that. And so, all of a sudden, we have a reason. These are reasons. We're going to have 2 reasons. Reasons to use a different stats analysis. Okay, that is, other than doing multiple t-tests. And one of those reasons is because we want to avoid inflating our chance of making a type 1 error. Okay? Everybody with me? So this is the conceptual. This is the conceptual. If I do multiple t-tests, each at this level, then when I get done with my entire analysis, I'm going to have inflated that chance of making a type 1 error. So I want to develop a test that avoids that inflation of making a type 1 error. Okay? We need to do something. We need to fix the problem, right? So one reason and we're going to have two reasons to use a different kind of a stats test, a different kind of an analysis than doing multiple t-tests, okay? One is to avoid inflating our chance of making a type 1 error. So we want to avoid something here. The other reason is a little bit more of a positive reason. I mean, that is, we want to do something to increase the efficacy, the usefulness of our test. We certainly want to avoid type 1 error, but here's the deal, and this is where I think talking about this more complex analysis helps to reinforce what we've learned about the t-tests. Okay? So let's not talk about that right now because we'll get to that. But let me ask you this question, right? Let's think about that t-test where we're comparing the two means, but remember what goes in here. This is our measure of variability. Of course, that's our central limit theorem, but we start with this, right? We start with this. We actually start with the sum of squares, but that gives us our pooled variability. Okay, so let me use a different color here, maybe it'll help. Let me focus on this t-test. Well, when I do this t-test, we use this formula, right? If you do this t-test, I'm going to use this mean plus this mean. Well, I'm going to subtract them, I'm going to compare them, okay? Mean Q minus mean for Taylor Swift here. And then in our denominator, we're going to put these sum of squares together. We're going to pool that variance. And the reason that we're pooling the variance from two groups is because now we have two guesses for sigma. Remember, that's what this gives us, our best guess for sigma squared, and then we do this central limit theorem. This is our best guess for the variability. I want to reinforce that concept, okay? And we pool this variability because we have this assumption of homogeneity of variance, right? And the assumption of homogeneity of variance is an assumption that's based on the fact that if we fail to reject the null, these two came from the same population, so we should pool them. If we reject the null and say these came from a different population, well, remember that even though the means might be different, the variability for those populations is the same. That's very, very important. Put an asterisk in your notebook. Rewind the video, okay? If we fail to reject here, then they came from the same population, and so we should be able to pool the variability to get our guess for sigma. If we reject the null, well, they came from different populations, but I'm going to assume that the populations have different means, but the variability is the same. So we're able to pool that variability. If I do this t-test, well, I'm going to compare this mean to this mean, right, with subtraction. And I'm going to pool this with this. And so on with our t-tests. But here's what we're going to do. I'm going to maintain that assumption of homogeneity of variance across all four groups. Okay? If all of the groups are equal, that is, they come from the same population, then I want to pool 1, 2, 3, 4 groups to get my best guess for this, okay? Even if I reject the null and I say this group's different from this group, different from this group, different from this group, I'm still going to assume that the treatment just pushed the curves around, but that the variability is going to be the same. So when I compare these two, what I want to do here is effectively pool all the groups together. I want to pool all the groups together. Even if I'm comparing this to this, I want to have a pooled measure of variability that includes all 4. In this case, right, I have 4 guesses for sigma instead of just 2. I have 4 instead of 2, so why wouldn't I use that, okay? And so the second reason that we are going to use a different statistic is because I want to pool the variability of all the groups. And by the way, we have 4 groups here. There are times when you might have 5 groups or 3 groups or 7 groups. Okay, this is generic. I'll show you the formulas in a little bit. This is generic to however many groups you use, more than 2. If you have 2 groups, use a t-test, T for 2. If you have 2 groups, then use a t-test. When you have more than 2 groups, that's when we get into trouble with inflating our error rate. That's when we have to think about pooling the variability of all groups to get our best guess for sigma, okay? And that's what this gives us, okay? Our best guess for sigma. So there are two reasons that we should develop a new statistical test to analyze more than 2 groups. In this case, we're using 4. The reason that we're using 4 is because it was dictated by the nature of our variable, okay? So that's a research methods, a research design issue. Once we collect the data, now we need to do our analysis in a way that's a little bit more complex, and I will show you how to do it, okay? T for 2, T for 2. If you have 2 groups, use a t-test, okay? If you have more than 2 groups, then you're going to do a different test, and that's what we're going to get to. And the reason that we're doing that is for these 2 reasons. Make sure you have this in your notebook, because I'm going to ask you to go back and look at it once we do the computations. We're going to look at, have we accomplished addressing these 2 issues, right? Have we accomplished what we set out to address? So we're not going to do multiple t-tests. That would lead us to, if we did multiple t-tests, we would inflate our type 1 error. It's called a type 1 error rate. The chances of making a type 1 error were going to increase. We definitely don't want that to happen. Also, this is sort of more of an approach reason, right? We have an avoid, we have an approach. Even if I'm comparing these 2 groups, these 2 means, I still want to pool all 4 group variability, right? In the denominator, I want my best guess for sigma. So we're going to pool all of this information, okay? So what I'm going to do, this is a shorter video, right? This is a shorter video because what I want you to do now is to get each of the 4 means, and let's get each of the 4 standard, sum of squares, and then we will work from there, Okay, we will work from there. So I'm going to end this video short, and you can do the computations, and it's a good way to check yourself to make sure you're doing this correctly. And the next video will pick up right from there.